Uh, Hello, good day everyone. Thank you for joining us today. Thanks to Mr. Ade Yoseman as our OWASP Jakarta Chapter lead and also Mr. Philippe De Ryck as our guest speaker. Today he is going to present about getting API security right. Mr. Philippe is web security expert and also founder of Pragmatic Web Security. Before we start, please use the chat box or raise your hand if you have any question. Okay, now I will going to record the session. Mr. Philippe, please.
All right, thank you for the introduction. So raising your hand doesn't work really well because I get a notification that you're raising your hand and I don't know why. So my typical mode of operation here is basically that you use the chat to ask questions. I have enough computer screens here to keep an eye on the chat. I'll see your question come in and I'll try to address it if it's relevant for what we're talking about. And if you have like broader questions or more elaborate questions, I recommend keeping that to the end because we should have some time for Q&A towards the end as well. And with that, I think we should get started. All right. So let's talk about API security. Let's talk about a couple of ways that you can actually improve the security of your APIs. And I'm going to work through it step by step. And I'm going to start by setting the bar for API security like really, really low. So the worst thing you can do basically, or one of the worst things you can do is this example right here from Harbor, which is a container registry. And that piece of software had a flag somewhere that said has admin role true. And you could basically set that flag. Well, if it was false, you could set it to true, and that would make you admin in that to that API. And that's pretty much as bad as things get. And I use this as an example, not to make fun of the people that built this, but to show you that these vulnerabilities are real world problems, to show you that these things are definitely out there and that is something that we should take into account. But I want to talk about more interesting things because honestly, setting Boolean flags to true, making you admin, that's not the most interesting case for developers. It's like, don't do it. And other than that, we're kind of done. And you might think that API security in the real world isn't that bad. It's like, yeah, these are odd one-offs. It's not that common. But this is unfortunately not the case. Here's a study from a couple of weeks ago, from February 2021. And that study looked at 30 e-health apps on mobile phones, so mobile e-health apps. And of those 30 apps, they found that 77% contained hard-coded API keys. And that's a lot. And that's a major problem because these are client applications using APIs and they have secrets embedded right in there. And if it's a JavaScript app, you can decipher the minimized JavaScript and get it out. If it's a mobile app, you can decompile it or just look for strings in that executable. And it's very easy to extract these things. And we know about these things in the security community because if you look at things like a mobile security top 10 or mobile security guidelines, one of the first things you'll see is do not embed secrets in that client application. Yet here we are, 30 real-world applications, sensitive data, hard-coded secrets in a lot of them. And it gets worse because the people doing this study also looked at the APIs behind these applications, and they found that every API that they looked at had authorization problems. It's called a BOLA attack, broken object level authorization, something we'll talk about in a second or in a bit more as a second in this presentation. But this just gives you an idea of how dire the current security landscape is, how difficult it is to build secure APIs and how common vulnerabilities are. And that brings me straight to my first takeaway here. And that first takeaway is that it's time for us as a community, as developers, as professionals to start taking security seriously. And I kind of make fun of this by saying the cowboy years are over, as in the time that you build something and you're like, yeah, we'll worry about security later when this takes off. That time has passed. I mean, we're dealing with massive amounts of data, very sensitive data from people, from customers, and we have a responsibility to build more secure APIs. And that means taking this into account from day one, not as an afterthought when you have some time later on, because guess what? That's never going to happen. And before you know it, you're running a massive application with APIs that you never really considered to secure properly. And that's something that we should definitely avoid from happening. And that's why I'm giving talks like this to help you get better in securing your APIs. Just a small word about me. I'm Philippe De Ryck from Belgium. I used to travel the world to help people build more secure applications, and now I basically do that from my home in Belgium because I'm not allowed to go anywhere according to the Belgian government, and they're kind of right with this global pandemic thing going on. So what do? I'm a web security expert, as Vina introduced me. So I'm running my own company called Pragmatic Web Security, and I mainly help other companies through developer training. So I do security training for developers. I do online courses on complex topics like OAuth and OpenID Connect, and I also do some security consulting, basically helping them with the knowledge that they need to make decisions to build secure applications. I'm a Google developer expert and an Auth0 ambassador, which means that these companies recognize me for the work I've been doing in the community, like presentations like this one. I'm not paid or affiliated with them in any way except for this outreach programs, just to make that clear, because sometimes there's some confusion about me working for Google, which is not the case. All right, enough about me. Let's talk about security. First case here, I'm going to use a lot of stories because this makes things like really real. It's not a fictional PowerPoint scenario. No, it's a real world application with a real world vulnerability. In this case, Bumble. Bumble is a dating app, and they had some premium features that you have to pay for, which is very common these days. And they also had some security mechanisms like lockout, and if you misbehave, your account gets locked and stuff like that. And it turns out that when people looked at this Bumble application, that these measures were mainly enforced in the client application, meaning that your mobile app enforces these restrictions, but the API behind that application is like, yeah, I know who you are. You're an authenticated user. That's good enough for me. And the API never checked restrictions, never checked whether you had a premium subscription, and so on and so on. And that's kind of bad because client-side security, security on the client is probably not the best way of doing things. And something similar happened to Twitter. A couple of months ago, in 2020, they released a feature called fleets, which are temporary tweets. I don't even know if people are using that, but whatever. But what really happened is, or what's more interesting here is that in that example, they enforced sending a read notification on the client as well. So they had an API to retrieve information from about tweets or fleets or whatever, and then the client, when it received that information, sent a notification to an API endpoint like, hey, the user has read this specific fleet. And somebody figured out that they could fetch the information without sending those notifications, which would essentially give them access to the data without Twitter being able to mark that as read and without tracking that, and so on and so on. So again, that's relying on the client for a security feature or the correctness of a transaction, and that's something that we shouldn't ever do when we're building secure APIs. And that brings me to the real the first real takeaway here. And the first real takeaway is the client is irrelevant for security. And I see this is a very common mistake, actually, because we believe, it's easy to look at the client like, yeah, that's a functionality here. That's what the client does. But the real functionality, the real attack surface is your API, all accessible endpoints. And I don't care as a security person, I don't care if your admin endpoint is never used by the client. If it's there and if it's exposed, it's part of your attack surface. And if you make a mistake there, if you have a vulnerability in that admin part of the API, it could be that someone finds out where it is and starts abusing that, which can create significant problems for your API. So the real attack surface, the real thing to think about when you have to secure an API is whatever you expose and forget about what the client does. Everything that the client does is irrelevant at this point in your security testing or security process. And that brings me to an interesting observation. Is the client really irrelevant? And what about client-side controls? We do client-side input validation and stuff like that. Isn't that useful? Isn't client-side authorization useful? Well, actually, it is useful for a couple of reasons. It's useful to build a clean user experience, because obviously if a user doesn't have access to admin features, there's no point in giving them a menu item admin features because they won't be able to do anything anyway. So that's kind of the obvious use case. But what's actually more interesting is that if you do your client-side authorization and input validation correctly, then your API endpoints shouldn't see malformed data or shouldn't see authorization failures for a specific user, because you're doing that in the client. And if you see that anyway, that means that somebody is probably messing around. Either you have a bug in your client, that's an option, or somebody's messing around with the API, and that gives you some information as well. So I have to come back to my first takeaway here and kind of refine that a little bit. And the refinement here would be that the client is irrelevant to enforce security. The client is still very relevant to as a first line of defense, as a way to ensure that legitimate users can only send you legitimate data and access legitimate features. So that's definitely a good thing. And it makes your detection mechanisms on the API side of things much more effective to find out when a user is behaving in a malicious way. All right. That's a first really important takeaway. Forget about the client. Well, make sure the client does things correctly, but forget about the client when you're analyzing the attack surface of your API, essentially. All right, let's talk about dating apps a bit more. Well, not sure if this counts as a dating app, but I'm gonna leave it in the middle how we see Grindr. But what's most interesting here is that Grindr had a kind of nasty flaw, a very, very subtle flaw. And what happened is that you could, well, Grindr has accounts like all applications do, and they allowed the resetting of a password. Very simple, very straightforward. You enter your email address and the Grindr backend sends an email with a link, and that link contains a unique token, which allows you to reset your password once, and off you go. The problem here that somebody discovered is that when you entered your email address, that was an API call to the backend sends the email and sends you an API response like 200 OK in return. And that response contained JSON data with the email address, which is not that uncommon. But it also contained that secret token that was used to create a link in the email. That token was being leaked in the API response, coming sent back to the front end, to the web application running in the browser. And that's called sensitive data exposure or data leakage in an API. And that's actually a really, really common vulnerability. That vulnerability basically means that the API is sending back more data than the client is using. So you don't see that in the client. The client is not going to show that token because the client is not using that specific piece of data, but the API is sending it back, exposing it to someone looking at the network traffic. And this often happens through the marshalling of objects. So let's say you're building an API in Java, and then it's very common to use a Java object for the password reset token, and then or the password reset response, and send that entire object back as JSON data. And that happens automatically in most frameworks. You just throw the object in the response and it automatically transforms it into JSON. And at that point, you'll have to mark certain fields in that object as non-exportable or non-exposed to JSON to ensure that this doesn't get sent to the client. And if you forget that, then you have a bit of a problem. And that's due to that object marshalling. So leaking data, obviously not good. Somebody can look at that and inspect that and maybe get that data out of there. But what if we can make it even more dangerous? What if an API not only automatically exposes data because it translates Java objects or whatever to JSON, but also accepts data that it shouldn't be accepting? That's kind of an interesting problem, right? And I have a couple of code examples or snippets to show you how that can happen in practice. So what's the feature here? The feature on the API is to change the name of the user. So I'm going to change my name to Dr. Phil because it's kind of a good name if you want to start a TV show, I guess. So maybe I'll want to do that in the future. So you send a request to the API. It's going to be a patch request. If it's a REST API with some JSON data, it says name is the new name, and the API will handle that. My API, in this case, uses a framework such as Spring Boot, for example, which has automatic transformation from JSON to Java objects, which is pretty useful. It's absolutely awesome. If you've ever done JSON parsing by hand in Java, you know what a freaking pain that is, and you love features like this. I mean, I get a user object in the request, and I get the fields from there. For example, the API will be like, hey, if the name is not null or not empty, then the user has submitted a new name, and we can actually update the name of the user. And that's how legitimate code would use this to update the name of the user. However, it depends a bit on how this is implemented, but very often APIs or frameworks like this also allow additional data because they don't really check that you only provide a name. They just check if the user is updated and then push that user through the persistence layer, and it will automatically get updated in the underlying database. So if you submit something like this, name something, LOL, email is an evil email address, doesn't matter here. And then we see a password field. And that password field in this case is a password provided by the attacker, and the vulnerability is that this will get stored in the database. So this allows an attacker to override fields in the database with their own values, allowing the attacker in this case to take control of anybody's account by resetting the password to something that they know, allowing them to log in with that account. And that's a nasty vulnerability. And that's the official name for this class of vulnerabilities is called mass assignment, because we're assigning fields that we really shouldn't be assigning, but because I can't really call it lost in translation, but something gets added in translation, basically, from JSON to Java or to .NET or to Ruby, if you use objects in Ruby, I don't know, but to anything, that's essentially the problem here. And this is a nasty vulnerability. What's the takeaway from this weird class of vulnerabilities? Well, you have to test your APIs. I call it in their natural habitat. So that's from nature shows if you want to dive into that. But essentially, this means that you can't really trust the code in your API. You can't really look at the code. You have to make sure that you test the full system. Like provide JSON, run it through that translation step, see what happens when you actually have that JSON turned into an object stored into your database. Runtime testing is absolutely necessary. Static code analysis will never find something like this, for example. Unless you know how to look for that, you will not find that by looking at code only. You have to test your API when it's running in your actual systems. Testing your API like that is useful, but also kind of tricky if you have to do that over and over again. And that doesn't seem like a very sustainable and scalable way to ensure the security of your APIs, right? And that's a correct observation. And that's fortunately something that we can kind of solve by using API contracts. So we have Swagger definitions, which turn into OpenAPI essentially. And with OpenAPI, you can, well, it's YAML, so it's ugly, but you can describe your entire API, every single aspect of that. You can see examples here. We have a restaurants endpoint on line 10. You can see that we define a GET request. That's on line 11. We have some description to generate documentation from this document as well. And you can see like, hey, if you send a GET request, you get a couple of responses. One of them has a status code 200, and that means that you get a list of restaurant names and so on and so on and so on. And if you have an API contract, then there's no confusion, no discussion about what the API is supposed to be doing, because the contract says exactly what your API is supposed to be doing. And if you write a contract that says like password reset, it returns the password reset token, then, well, that's a problem in your contract, but you can now see that it's visualized. You can see that problem. If you accept a password when somebody updates the user account, you accept a new password like that, it's now visible in the contract. And if it's not in the contract, then you can use tools, fuzzing tools, to actually compare your API or test your API against the contract. And these tools can actually find quite a few of these vulnerabilities automatically because they have the exact API definition in that contract. So here's just two examples, and you can find more advanced products as well. These are free and open source examples. By the way, a lot of commercial vendors also rely on these contracts to enforce security. So you'll find API gateways that take a contract, and that allows them to see if a request is carrying more data than it should and block that request, and so on and so on. So this is actually a really important item. And it's not that difficult. It takes some getting used to the way to write these things, but there's tool support for that. And once you get that integrated into your process, you have a clear way of defining your API. And that's actually highly recommended to start doing that. So it's called OpenAPI. That's the latest version. Swagger is an older version, but I'd added a name here because most people still know Swagger and not really know that turned into OpenAPI. All right. Good. So now that we know that our API does or doesn't accept more or doesn't expose more than it should, let's talk a bit about other problems that can pop up down the line. And one of these problems is authorization. Again, real world story, T-Mobile. T-Mobile is a mobile phone operator, and they allowed you to retrieve your account information by calling their API with your phone number as the identifier. So we'd call the API with, I would call the API with my phone number, and they would return my information. And you would call that API with just call that API with any phone number, and the API was, oh, you're not authenticated. That's not good. So they had security in there. They had authentication built into their API, but they didn't check whether you were the actual account owner. So if I send a request to retrieve my information with my phone number, I would get that. But if I would send a request with your information and I was logged in with your phone number, I would get your information. And that's what we call an insecure direct object reference. That's the old name that we had in non-API applications, and in the API world, we now call that BOLA, or broken object level authorization. So what's basically happening is, well, I have a code example of how that happens in a second, so I'm going to show that in 2 slides. T-Mobile is not the only one with this problem. So T-Mobile is a phone operator. They use phone numbers as identifiers, which kind of makes sense because they're unique, so why not do that? But Telefonica in Spain had the same problem. Verizon in the US, AT&T, a lot of companies have this problem. And it goes beyond phones as well. Here's an e-health patient portal in India that has this exact problem. We have Twitter that had a problem like this, allowing somebody to match phone numbers to user accounts. And Facebook had something like that, where you could just update the name for any Facebook page. So I could rename the OWASP Jakarta page to something else and then create a new one with that name, and I would take control of that page, essentially. And a certain person called Marcos discovered that, and he earned $15,000 for reporting that vulnerability to Facebook. So these things exist in real-world applications, and they're everywhere. And the reason that they're everywhere is because they're really, really hard to spot. Unless you know that you have to look for that, it doesn't jump out and say like, oh, this is so insecure. No, you have to look for something that's not there, and that's kind of tricky. And that's why I have a code example here, just to illustrate to you how easy it is to introduce such a vulnerability and how difficult it might be to actually find that problem. So this is Spring Boot code example. Very easy, very straightforward. But even if you're not using Spring Boot, I'm sure you can understand what this means. That's the benefit of Java. It's very verbose, so you can read that and kind of understand. So Spring Boot typically handles authentication or authentication checks on a global level. So all endpoints require authentication. That's good. And then you can also see on line 1 that we have a pre-authorized annotation. And that kind of means that we are requiring the user to have permission to edit restaurant information. This is a restaurant review application that I use for trainings. And that's good. That permission check ensures that the user that doesn't have that permission cannot access this endpoint or execute that code. So that's awesome. What's not here is a check to see if the user is actually the owner or the manager of the restaurant that they're updating. So we check the permission to edit restaurants, but I can edit restaurant 1, 2, 3, 4, 5, 6, all the way to 99,999. And that's BOLA. There's no check here to check if the authenticated user has permission to update this particular restaurant. And that's exactly the problem that appears in all of these APIs that I talked about before, and that appeared in every single API of those e-health applications from the study I mentioned all the way in the beginning. So again, real-world vulnerabilities, real-world problems. You have to look for this because there's no insecure line of code here. There's a missing check to see if the user, the authenticated user, and the restaurant, if there's a relationship that allows the added restaurant permission for that particular restaurant. And that's what should be here. And that's something that is often missing in APIs. So you have to implement a sound authorization policy. That's essentially what this is about. Checking authentication is only a first step. You have to have an authorization policy, preferably in kind of a centralized location, so it's easier for you to audit that policy to make sure that it does what it is supposed to be doing. All right. But where do you get authorization information? Well, it's an API, so chances are you're using tokens for that. There's nothing wrong with tokens. What kind of tokens? Well, usually JSON Web Tokens. Whether you like it or not, that's kind of the de facto standard for representing tokens these days. So I really want to talk about JSON Web Tokens for a couple of minutes here as well. Here's a simple JSON Web Token. Usually JSON Web Tokens have three parts: a header, a payload, and a signature. But in this case, you can see in the header that we have specified ELG none. And that's a first problem with JSON Web Tokens that we really have to talk about. ELG none means this JSON Web Token is not signed, which seems ridiculous because if you don't sign a JSON Web Token, and I'll talk about signature schemes in a couple of minutes, but if you don't sign them, then the data is not protected. And anybody can go in here in the payload, the purple part, and change whatever they want. And the receiver of this JSON Web Token will not even see that this is invalid data. They won't even know that the attacker changed some data here. And that's a bit of a problem. ELG none is in the spec, but nobody in their right mind is going to create tokens with ELG none as a signature scheme. So why is this a problem then? How come that this results in a problem if nobody generates tokens like that? Well, because even if you generate JSON Web Tokens with a signature, your libraries at least used to accept tokens with ELG none. So most people use libraries to handle JSON Web Tokens, which is one of the strengths of that ecosystem. There's hundreds of libraries available, which is awesome. What you want to avoid is using a library from 2015, because this is when this vulnerability was discovered and fixed. Because then what happened in 2015 is that if you send a valid JSON Web Token, one from the service with a signature, the library would check the signature. But if you send it a malicious token and you said ELG none, the library would be like, oh, ELG none, so no signature check, cool. I'm going to just return the data, and the API would accept that data. And I can hear you like, yeah, we're not using libraries from 2015. And my response is like, are you sure? Have you checked that? Because some companies apparently still do. Here's a story from 2020 from OutZero. They actually had this exact vulnerability in their APIs because they were still using old libraries. And they implemented a check. There was a line of code somewhere that said, like, if ELG none, reject the token. But the check was case sensitive. So if you provided ELG none with different with capitalization, like one capital E, the check wouldn't trigger, and you would actually be able to bypass the check. The library would still fall for that vulnerability. And when I explain this, people are often like, yeah, sure, there might be some old dependencies. I'll check that. But I'm pretty sure that we don't do that. And when we don't introduce or don't use these old libraries, then we're probably safe, right? I mean, nobody implements vulnerabilities like this in modern systems. Well, surprisingly, even in modern systems, this still happens. Some people hate these vulnerabilities so hard that they built a website that says, how many days since a jot elgnonvuln.com, which doesn't really write well as a URL or to speak well, but sure. The latest case, at least a couple of weeks ago, I didn't check today, sorry, but the latest case back then was the UK NHS COVID-19 contact tracing app. So you can say everything you want about legacy code. I'm pretty sure that this code has only been developed in the last year, yet it contained this exact vulnerability where it accepted ELG none JSON Web Tokens. So this is not a vulnerability from the past. This is something that still happens today and something that we really have to test in your APIs. Avoid custom jot validation code. Don't write your own code. Use an up-to-date library and write a test suite to ensure that your up-to-date library rejects tokens with ELG none in all forms of capitalization. Better for you to find this vulnerability during testing than for an attacker to find it during their testing or during production, basically. All right, so how do you sign JSON Web Tokens? What can we do to make that better? Well, one of the ways to handle JSON Web Tokens is to use an HMAC signature. And an HMAC, well, if you use the JSON jot.io website, you get a decoder. So the encoded version of the jot is on the left. That's base64 encoded, basically. And the blue part at the bottom here of that encoded version, that's an HMAC signature. And that's generated with a secret. And because of that, we can verify the integrity of the data. So let me show you what that looks like. We have a backend system, and that backend system has an HMAC secret, and it's going to use a cryptographic function to generate that HMAC. Typically, that's all embedded in your JSON Web Token libraries, but I'm going to explain to you how it works conceptually so that we can understand its security properties. What is the input there? A JOT header and a payload. That's the data that we want to protect with the HMAC. And we also provide that secret value as input. On my previous slide, that was super secret HMAC key. All right. With that input, the HMAC function spits out an actual HMAC, which is also known as a keyed hash. Doesn't matter how it works, that function. What matters is that this HMAC is linked to the data and the secret. And that's essentially what the JOT library attaches to the JSON Web Token. So we have the header, the payload, and the HMAC. That's the JSON Web Token that we can send to a client. So at some point, we get it back from the client, and we want to ensure that the data that we have sent to the client hasn't been modified by a malicious user. That's essentially the goal of adding that HMAC here. So whenever we receive an HMAC, we're going to recalculate, or a JOT, sorry, we're going to recalculate that HMAC by giving the header, the payload, and the secret as input, and out comes a value, a new HMAC. Next, your library will compare these HMACs to each other. We had the HMAC attached to the JSON Web Token, and we have the new HMAC. And if these are the same, then we know that the inputs to that HMAC function haven't changed. So we know that the data is the same, and we know that the secret is also the same. So we know that nobody messed with the data, nobody changed the flag from false to true or something like that. If something goes wrong, if there's a difference, then either the data or the secret is different, but we don't really care what it is. We just reject the token and throw it out. And that's essentially what happens under the hood when you use an HMAC to protect the integrity of the data in a JSON Web Token. This is also the mode of operation that you'll find in a lot of tutorials and blog posts and presentations like this one, and so on and so on. But there's a very big limitation here. And that limitation is that the secret used to generate an HMAC and verify an HMAC is the same secret. And that means that this mode of operation with HMACs is only useful in a single isolated service. You can never use this, or at least not securely, in a distributed scenario, because you'll have to give someone else, if you're the generator, you have to give the verifier that secret. And with that secret, the verifier can start generating validly signed JSON Web Tokens themselves. And that's kind of a limitation. That's something that you want to avoid from happening. So in practice, I would say that HMACs don't really have that much of a valid use case, but there's a different mechanism that we can use, which I'll explain in a couple of minutes. That's one problem with HMACs, but actually the rabbit hole goes a bit deeper. Here's the example from before, and I told you that my HMAC secret is super secret HMAC key, as you can see right here. Your secret should, first of all, not be based on dictionary words. That's not the best way of doing that. And second of all, you shouldn't really publish that on PowerPoint slides, not even in talks like this. I trust you're all fine people, but still, I should not be giving you my HMAC secret. And this indicates a bigger problem because this is on a PowerPoint slide. It's an image, so it's hard to copy paste. But if I would give you a code example on Stack Overflow, that's easy to copy paste. And somebody looked into that, a company called Wallarm, and they built a list of commonly used HMAC secrets for JSON Web Tokens that they found in tutorials, in blog posts, on Stack Overflow, and so on and so on. And they found that a couple of production systems were actually using these exact secrets. So they built a tool that you can add to Burp, which is a pen testing tool, that will automatically monitor JSON Web Tokens and see if it uses one of these weak secrets. And this is absolutely ridiculous. Because if the attacker knows your secret, they can generate valid JSON Web Tokens with arbitrary data. And if you have a flag admin false in that data, which is integrity protected, well, the attacker now can make admin true, recalculate the HMAC, and your API will be like, ooh, that's valid. Boom, vulnerability. Absolutely insane. If you can use weak secrets, well, somebody can also start guessing your secret. So if I have one JSON Web Token from your application, I can just guess what the secret is and try it out. And if I get the same HMAC than the token actually has, then I know that I found your secret. So some people have figured that out as well, which shouldn't be a problem, but because people use weak secrets, use predictable or text-based secrets or shorter secrets, this is a bit of a problem. To be fair, the spec covers this. The spec says like, yeah, you should use long and random secrets for your HMACs, but in practice, people don't do that all the time, which creates a potential vulnerability. So the takeaway here is that JSON Web Tokens have way more issues than they should have. It's not that great that I have to explain all of these things when I'm talking about JSON Web Tokens to developers, but it is the reality here. But to be fair, if you follow a couple of guidelines, which I'll discuss next, the use of JSON Web Tokens is actually not that bad and can be done quite securely. So let's try to address these issues, shall we? First of all, what you should be using is not HMACs, but public-private keys. If you use proper digital signatures, such as the RS256 or PS256 signature scheme for JOTs, the story changes a bit. The mechanism is still the same. We have the header and the payload that we will protect with a signature, but we now generate a signature with a private key. So the service generating the signature has a private key, and out comes that signature value, which is attached to the JSON Web Token. Very simple, very straightforward. It gets better though, because to verify a signature, we now use a public key. And the public key is the public key that the public key is uniquely linked to the private key. So we use a verify function and we feed the public key, the data, and the signature into that verify function. And out comes the result, true or false, exception or no exception, or whatever your language likes to do. If we end up in the green part, the valid result, then the data is the same. The data hasn't been changed by a malicious user. And we also know that the signature must have been created by the private key that belongs to this public key. And if something is different, then either the data has changed or the wrong key has been used. That's essentially the message. And this mechanism becomes much more scalable and much more effective in a distributed scenario. We all use this all the time, by the way. If you, for example, use login with Google somewhere, you're using OpenID Connect behind the scenes, and OpenID Connect uses exactly this scheme. Without going into the details, when you use login by Google or login with Google, Google will eventually issue an identity token with your account information in there and sign that with Google's private key. And every application that integrates login with Google pulls in Google's public key. It says like, oh, Google's public key is this key, and they can verify that this token is actually, this identity token is issued by Google because they verify that it's signed by Google private key with Google's public key. And that's essentially how this works in practice. And the public key, as the name says, is public information. You can literally put that on your website, on your Twitter profile, wherever you want, or in an OpenID Connect configuration document if you use OpenID Connect. So the takeaway here is that if you're using JSON Web Tokens, use the correct JSON Web Token signature scheme. My advice is that HMACs typically are not the right mechanism. They're easier to implement, that's true, but it's not that public-private keys are that hard to implement. So my advice is take that little bit of extra effort and implement the correct signature scheme, because it's going to save you a lot of headaches down the line. There's no brute forcing. You're not going to put your private key on a PowerPoint slide, because that would not be very pretty either. And it's a long key. So there's all kinds of benefits, especially if you use distributed scenarios, because only one party has a private key, the issuer, and everybody else can have the public key, which is irrelevant or not security sensitive, I would say. There's a lot more JSON Web Token best practices, but well, I'm kind of guessing that you don't want us to be here all afternoon, if it's afternoon for you, or all morning. So I'm going to have to cut it short here, but I'm going to give you a couple of pointers and a very useful reference. So essential best practices: use private keys instead of HMACs. We covered that. Obtain your JSON web key, a JSON key material, JSON Web Token key material, your JOT keys, the public key in this case, using an out-of-band mechanism. So there's mechanisms to drop keys into the header of the JOT. That's a really bad idea, because you don't know whether you can trust that information before you have verified the signature. And we see some vulnerabilities that rely on that data anyway and cause problems. So what OpenID Connect does, for example, is you fetch the keys from a server from Google from a very specific location. And it's always in that location, whether you log in with Google or you log in with GitHub or whatever. It's always in a folder called .wellknown/OpenID configuration. That's the file, and the key material is listed in that file. no questions. Third takeaway, use explicit typing for your JSON web tokens. And explicit typing means, let me skip back maybe a slide to illustrate that. If you have a JSON web token, like this one here, there's a type header that says JSON web token. And that's very unhelpful. It's like, yeah, I kind of knew that this was a JSON web token. Thank you anyway. What's the latest recommendation here is to avoid token confusion attacks, is to make that type explicit. So if it's an access token in the OAuth world, then this will become AT plus JWT, saying AT for access token plus JWT. If this is a custom token for your application, you could call that super cool application plus JWT, and then you know that this is an exact token for your application, and nobody can try to confuse an API by sending it a token for a different purpose. So the explicit typing kind of includes the purpose of the JSON web token right there in the type header parameter to avoid confusion. If that wasn't really clear, or if you're like, yeah, that's a bit short, do you have more information? Yes, I do. There's a document, an RFC called RFC 8725. And in human language, that means JSON Web Token Best Current Practices. And it's actually a really, really simple RFC, so don't be afraid of looking it up. It has two sections. Well, there's some meta sections as well, but basically it's a list of common vulnerabilities with JSON Web Tokens and a list of implementation guidelines that you should be following. And some of these guidelines that I discussed here come straight from that document. So if you're doing anything with JSON Web Tokens, this RFC should be something that you know by heart and that you follow closely in your application code. Takeaway here, follow JSON Web Token best current practices. Use JSON Web Token sensibly, write a battery of tests. I don't care that you think that you know how your code works. I want to see test suites to do that. Yeah, my library doesn't accept Alkanon. Well, sure, I believe you, but test it. Show me the test suite, and only when all the tests succeed or fail, depending on how you write them, then I'll believe that your application actually doesn't accept that. And this is really, really important because sometimes your library or framework does something that you don't expect, and if you don't test it, you will never know until somebody comes and tells you that they find a problem or a vulnerability, or they actually exploit that and extract data from your system. All right. As much as I love talking about security, which I actually do, it's kind of my job as well. We have to stop somewhere, and that somewhere is kind of here. So my final piece of advice is that it's up to you now. I can talk about security all day long, but you're the people building applications, building APIs. So you'll have to actually start taking security seriously and convince your boss that you have to spend time on security if that's necessary as well. 3 concrete action items that you can actually start working on today or tomorrow, Monday, whenever you work. Audit your API authorization policy. So often, authorization problems are there, but they just don't jump out. So you have to carefully audit every authorization decision. Like, how do we make this decision? Do we know which restaurant we're making this for, which user, which whatever? And that's really, really important. I want you to write security testing to verify your authorization logic and your JOT handling, because these are very common problems, areas that we often see mistakes, and security testing is the best way to find it now or in the future. You never know when a new colleague joins, when you have a bad day and you create a vulnerability. If you have that suite of tests, it will catch that and tell you about that immediately. And then the third concrete action point is build OpenAPI definitions, write those specs, that API contract to specify the exact behavior, not only for yourself to understand your API and to make sure you have a reference, but also to feed that into security tooling that can actually rely on that API contract. And that kind of tooling will only become more important in the future. So better to start doing that now so that you're ready to start using that for security in the future. And with that, I want to thank you for being here. I hope you enjoyed the talk. If you have questions, we can definitely answer a couple of them right now. And otherwise, I suggest you follow me on Twitter. It's good for my social status if I have more followers, but also I tend to tweet very useful things about security and not about a lot of other crap. So definitely a good source for security information. All right. Thank you very much.
Thank you for your great presentation, Mr. Philippe. From the chat box, I already write some question. If there is an important case, do you prefer to do an escalation according to the procedure or do an immediate response? For example, sending the API keys to your developer so they can start debug on the production. In this urgent case.
Well, I would say there's not really another answer than you should follow procedures. The question is, are your procedures useful and do they actually work? So just running things like the Wild Wild West, just throwing API keys around like, yeah, you can just debug production, that's basically asking for disasters, because at some point things will go wrong. How do you send that API key? Like, yeah, it's typically like just Slack it to someone else. And all of a sudden somebody gets access to your Slack channel later on and they find that API key there and something like that. So no, I'm not a big fan of just winging it and seeing whether things work out, because they might for a while, but eventually this will really come back and bite you. And trust me, scrubbing resources like Slack channels and repositories and all of that for secrets is a really, really nightmarish thing to do. And it's something that you can probably never, ever fix again. So my advice is to, even as painful as this, always stick to the right way of doing things. But of course, you'll have to make trade-offs at some point, but try to make the right trade-off to make it usable for you, but to also kind of follow security best practices.
Okay, the second one. What is the important process in risk assessment to prevent API leakage? Do we need it before deployment process?
Well, if you work with API contracts, then you kind of build that in from the start, right? So you write, typically when you do API development with a contract, you start by writing the documentation first. You write out your OpenAPI spec, like, hey, this is what my API is supposed to do. Also a very great tool for inter-team communication, because if different teams build the front end and the back end or the APIs, then having that contract is definitely going to make everybody's life easier. So I would say it's way before deployment. This is something that you have to do in development, in testing, and it will run all the way through your lifecycle, all the way to deployment and securing that deployment. Because, for example, API gateways can take an API contract as input and then start protecting that API at runtime. So yeah, it plays a role in all these aspects.
Okay, thank you, Mr. Philippe. It's all clear. So if there anyone who want to ask directly to the speaker, you can please to do so. Oh, we have another question from Team Fazer. I want to ask about Means Web Proxy and Express.js API. There's a function to specify the payload and stuff in Means. Is that one of security feature that you can mix to make sure the algorithm equals non-stuff?
I'm not sure. I'm not sure about the question. I'm not sure who's doing what there and what you're aiming at.
So in this Express.js API, we are using Express.js. There are a function to specify the payload and stuff in Means. Is that one of security feature? Yeah.
So I would say you can always build a layered security defense, right? So one of the things you can do is you should first of all ensure that your Express.js API doesn't accept ELK non-tokens. That's step one. I mean, everything else is just patchwork. So make sure your API is actually secure by using up-to-date libraries and by writing a test to ensure that this is handled correctly. A second layer of defense could be, as you suggest, you could use proxies, reverse proxies like an Nginx or an API gateway to detect, or even a web application firewall to detect ELK non-tokens. And you could block it at that level, but it shouldn't matter too much. I would say I wouldn't focus on that too much because it can give a false sense of security in some cases, unless the API endpoints are really resource hungry, then you can actually shield them a bit as well. But what you want to avoid is creating an ecosystem where a developer that hears about this and they run a test like, oh, it doesn't work on our API because your Nginx is blocking it. And then you deploy your API not behind an Nginx, but on Amazon, and there's no such protection on Amazon, for example. And all of a sudden your API is vulnerable because you're no longer blocking that type of behavior. That would be a problem. So always focus on the core, the root problem first. Fix your API, and then you can add additional layers of security on top of that to try and reject invalid requests as soon as possible. That would be a good strategy, but I wouldn't reverse it because that can create a problem down the line if you want to change your infrastructure, basically.
Okay, I think it's quite clear for the participant, and thank you for your question. Is there anything we can do for you? Oh, we have another question from Sevalda. What are the typical runtime tests that can cover common vulnerabilities other than what has been explained?
Yeah, if I would have a good answer to that, that would be awesome. That's the thing. That's the problem with it. There's no easy, as far as I know, easy test suite you can just run that will find vulnerabilities for you. So some of these are automatable, which is ongoing work, ongoing research, but in general, you're still responsible for writing these tests, and you'll have to look into the vulnerability and then find or write a test suite to cover the cases there. So mass assignment, you can test that. You can, an endpoint to update the name, you can provide more data and see whether that gets rejected or not. But to get that right, you would have to write a test for every field in that object, and so on and so on. And that's why these automation tools are so important. But this is definitely something that will evolve in the future, but we're maybe not there yet. So for now, it's just basically your responsibility to write these tests and get that up and running.
Okay, is that clear, Ms. Safalda? Okay, that's clear. I think we have the last minute here. So before we end the session, I would like to ask the participant to turn on the camera and we can take the photos together. Please turn on your camera.
If you're wearing clothes, that is. Otherwise, maybe not.
Yeah. Oh, it's disabled. Okay. Okay, now you can turn on your camera. Others, please don't be shy. Yeah, okay, we are waiting. I hope this meetup can bring somewhat knowledge for you, and I hope this will be useful for us for the implementation on our works. Okay, let me take it. Okay, thank you. You can turn off your camera now. Okay, I think we are at the end of our session. Thank you for your presentation, Mr. Philippe. Thank you for your attendance, all of the participants. We can meet again at the next meetup. Please don't hesitate to write us some feedback. I already sent you the feedback form on the chat. Hope you have a nice weekend and stay safe, keep healthy, and see you at the next event. Thank you. Bye-bye. Thank you, sir.
You're very welcome. All right. Thank you for hosting, and we'll hopefully meet again somewhere soon in real life. That would be awesome. We'll see how that goes.
Okay. Thank you very much.
Bye.
Bye.